All right, let's start. So 2.1, we're talking about convergent sequence. It's our first introduction to the idea of a limit. So 4 major definitions in 2.1 that we need to get, and then the rest of it is just proofs. So we need to understand the definition of sequence. Sequence, just an ordered list of numbers. How many are in there? 1 for every natural number. So a sequence is just a function from the natural numbers to any real number. The next big notion we need to get is a series. The series is going to be, we create a sequence from a sequence by summing up the first n terms. Then the next big definition is convergence, and then our last definition is going to be the definition for a limit, which if a series converges, it converges to the limit. So let's go over a sequence again, start from the top. So a sequence of numbers is a real valued function whose domain is the natural numbers. So it's a function that maps every natural number to some real number. Whatever we map 1 to is the first number in the sequence. Whatever we map 2 to, we call the second number in the sequence, etc. So if f is 1 goes to 1, 2 goes to 4, 3 goes to 9, 4 goes to 16, 5 goes to 25, etc., this is a sequence because we're mapping every natural number to some number, right? And we can represent the sequence as f of n is just n squared. How do you get the right-hand value from the left-hand value? You square it. That's what this is doing. The same way that we typically use f of n or f of x or f of something for the right-hand value of the function, when it's specifically a sequence, we like to use a sub n. How do I get the right-hand nth term from the left-hand element? You square it. So this, and this are all saying the exact same thing. Now, because we always know that, well, since when we have a sequence, we just really care about the right-hand elements, the 1, the 4, the 9, the 16, etc. We don't really care about the left-hand elements. We just write down the right-hand elements. No, this is not a set. We're using identical notation. There's no reason for you to know that this is a sequence instead of a set other than I'm telling you. This is not a set. Order matters here. 1's the first element, 4 is the second element, 9's the third element. This and this are capturing the exact same thing. Different way of writing the sequence, or we might write it like this. It's a sequence of n squared. What's the first term in the sequence? It's what you get when you plug in 1. What's the second term in the sequence? It's what you get when you plug in 2. What's the third term in the sequence? It's what you get when you plug in 3. You see how you can construct this from this? How they're the same thing? So that was a sequence. Some examples of sequence. If I say, look at the sequence 1 over n, what is that? That's 1 over 1, 1 over 2, 1 over 3, etc., etc., etc. That's the sequence 1 over n. If I say, let's look at the sequence m plus 1 over n, what's the first term in there? What do you get when you plug in 1? You get 2 over 1. What do you get when you plug in 2? You get 3 over 2. What do you get when you plug in 3? You get 4 over 3. 5 over 4, 6 over 5, etc., etc. So those are some examples of sequences. Now we're going to look at how we can get a series from a sequence, or a way we can construct one sequence from another sequence. So let's look at a sequence. We're going to say an is just 1 over 2 to the n. So what's the first term in the sequence? 1/2. What's the second term in the sequence? 1/4. The third, 1/8. The fourth, 1/16, etc. Understand the sequence?
Is that 2 times n?
Yeah, 2n. Plug in 1, you get 2. Plug in 2, you get 4. Plug in 3, you get 6. I did this again.
Yeah, I was wondering.
Thank you.
Not
2
8.
to the n. And for some reason, I keep doing it 2 times n. 2 to the n. Okay, that's better, right? So the next term in this sequence would be 1/16, 1/32, etc. Okay, now does the sequence make sense? Here's the sequence. Now we're going to construct a new sequence from this sequence. The first term in our new sequence is going to be adding up the first 1 terms. So it's going to be 1/2. The second term in the sequence is going to be adding up the first 2 terms. So it's going to be 3/4. The third term in our sequence is going to be adding up the first 3 terms in this sequence. So 7/8. Huh?
Why?
Why? It's a special type of sequence. So when I construct this sequence from this sequence, we have a special name for it. That's called a series. Okay. So it's just a definition. So I'm giving an example, then we'll read the definition exactly. So here's a sequence 1 over 2 to the n. I'm going to create a series from this sequence. How do I do that? I say let C of n, let the nth term in my new sequence be the sum of the first n terms from this sequence. So C of n is 1/2, the next term is 1/2 plus 1/4, the next term is 1/2 plus 1/4 plus 1/8, the next term would be 1/2 plus 1/4 plus 1/8 plus 1/16. We're just adding up the first n terms in this sequence to get the nth term in this sequence. Make sense? Okay, so this is exactly what we mean by a series. So if I have a sequence AN, I can create a series CN defined this way, where the nth term in my series is the sum of the first n terms in my sequence. And that's exactly what the definition is going to say. So given a sequence AN, define a new sequence C of n by the nth term in Cn is equal to the sum of the first n terms in AN. Then Cn is an infinite series. We say it's infinite because, remember, a sequence is from the natural numbers to the real numbers. So a sequence has infinitely many terms. And a series, the way that we've just defined it, is also going to be a sequence. So it's going to have infinitely many terms. For those of you who did like college algebra, you would have come across finite series, right? Ones that eventually terminate. This has no last term, in other words.
We had infinite series as well.
Right, but in here we're not going to worry about finite series. We only care about infinite series. So then Cn is an infinite series. The nth term of Cn is called the nth partial sum. So I sum up part of this sequence. That's my nth partial sum. If I sum up the first n terms in here, so if I sum up 1, 2, 3, 4, 5, I sum up these 5, and I get 31 over 32, then that's the fifth partial sum of this sequence.
But you can never find an exact number for the nth partial sum.
We can't figure out what this would eventually equal? What do you mean?
I mean, like, exactly what I just said. The nth partial sum, you can never find a number that equals that. Right?
So the first partial sum of this sequence is just 1/2.
I understand that. I'm saying for the nth, we can never find an exact number.
Are you saying for nth is just an arbitrary number,
Right.
and we can because we just use this. The nth partial sum is just going to be whatever the sum is. So it's that number. Okay. So that's a sequence, that's a series. Series is just adding up a sequence, basically. Okay, the big definition. This is one of the 4 big definitions in this class. Convergence. A sequence AN is said to converge to some number A, provided that for every positive real number, for every epsilon we always think about as a really small positive real number. So for every positive real number, there exists some natural number such that our sequence is within epsilon of A from that point in the sequence onwards. It's a really dense definition, so let's try and draw a picture real quick. So I've got some sequence, A1, A2, A3, ... Eventually we get to A sub big N, whatever that number is. A sub big N plus 1, ... goes on forever. There's infinitely many terms in it, right? A sequence has infinitely many terms. With me so far? So, if this sequence eventually converges to A, what's the intuition for what we're saying by that? We're saying this gets closer and closer and closer and closer to some number A. So, for example, when we were looking at this sequence, 1, 1/2, 1/3, 1/4, 1/5, 1/6, 1/7, 1/8. As it keeps going, what's it getting closer and closer to?
0.
0. So this definition is saying it converges. The A here would be 0. We're saying that this gets arbitrarily close to 0. What about this one? 2 over 1, 3 over 2, 4 over 3, 5 over 4, 6 over 5, 7 over 6. What's that getting closer and closer to?
1.
1, right?
Yeah.
A term in this sequence is going to be something like 1, 0, 0, 0, 0, 0, 1 over 1, 0, 0, 0, 0, 0, 0. Right?
Yeah.
That's going to eventually be a term in the sequence if we keep writing it out long enough. When n is this number, plug it in, that's what you get, which is absurdly close to 1. So that's what we mean by converge. We mean it gets arbitrarily close to. It gets really, really, really close to. It tends towards. That's all terminology that's sometimes used. So I've got this sequence, and let's say it keeps on getting closer and closer and closer and closer to some number a. What does that mean in the picture? Here's a, and we're saying for any teeny tiny epsilon you pick, doesn't matter what it is. So here's a plus epsilon, here's a minus epsilon. And we're really, really zoomed in. Epsilon is just a teeny, teeny, tiny positive number. We're saying eventually, if this series, or sorry, if this sequence converges to A, so A1, A2, who knows where those are? Here's A100, here's A101, and you keep going, you call all the possible A's that there are. Eventually there's going to come a number, A sub n, such that from this point in the sequence onwards, A sub n plus 1, every other point from here onwards is going to be within epsilon of A. So I'm saying for any epsilon you pick, for any cushion you put around A, for any epsilon you pick, I can always find an index in the sequence, a point in the sequence, where from that point in the sequence onwards, we're always in this little interval. Yeah, it's dense. So here's what we'll do. We'll do an example working with it, then we'll come back to a picture to try and recapture the definition. Because it's just a really dense definition. There's just no way around it. Okay, so let's do a proof real quick. And then we'll do two proofs with the intuition. So our intuition tells us this gets closer and closer to 0, this gets closer and closer to 1. Let's do those two proofs real quick, and then come back to the definition and try and make sure it makes sense. So, proof. Let's prove that 1 over n converges to 0. Right? So I need to show that for any positive number you pick, I can find a point, I can find an index in the sequence. If we write this out, remember this is representing an infinite sequence. I can find a point in the sequence where from that point onwards, the sequence will always be within whatever positive number you chose of 0. In other words, you say, you're telling me that this sequence will always eventually be within 0.000001 of 0? I'm saying yes. Alright, let's see it in action. So, 1. Let epsilon be any positive real number. We think in our head, epsilon is really something like 0.00001. It's a really, really small positive number. Doesn't matter what it is. For any positive number, epsilon, we'll think in our head something like this. Let epsilon be any positive real number. 2. By the Archimedean property, remember there's two versions of the Archimedean property. The Archimedean property says for any number you can think of, I can always think of an actual number bigger, and for any number you can think of, I can always think of a natural number so that 1 over that natural number is smaller. Remember? This ringing bells? Triggering memories? So by the Archimedean property, I know that there exists some natural number, I'm going to call it big N. There exists some natural number, big N, such that 1 over n is less than epsilon. That's what the Archimedean property tells us. For any positive number you pick, I can always find a natural number such that 1 over n is less than epsilon. So, coming back over to our thinking in our heads, so we're pretending epsilon is some really small number like that, then n would be some really big number, like, here's 1. Right?
Right.
1 over this is smaller than this. And it doesn't matter how small the number you pick, I can always find an n that makes this inequality true, right? You can't ever think of such a little number that I can't find such a big natural number such that this is true. Does that make sense?
And we proved that like 2 weeks ago, 3 weeks ago.
Yeah, that was the Archimedean property. So that would go back to our, I don't know if that's our first lecture, that's probably our second lecture.
Yeah.
So that goes back to lecture 2. Okay. So now I know that there is some natural number n such that this inequality is true for n, right? Now, what else do I know? If I make the denominator bigger, I make the whole number smaller, right? 1/3 is smaller than 1/2. 1 over 100 is smaller than 1/3. The bigger I make the denominator, the smaller I make the number. So I also know observe that 1 over little n is going to be less than or equal to 1 over big N for all n greater than or equal to big N, right? This is always going to be less than or equal to this if the denominator is always greater than or equal to this denominator.
Why are you using the same number or the same letter? It's so confusing when you get it.
Sorry, I'm just trying to make sure that you understand they're natural numbers. That's why I keep using n's.
Okay.
But I don't have to. It's just the way it is in the definition and in your book, so I'm trying to follow that convention. So this is, big N is some natural number. It's the natural number that makes this inequality true, right? And then little n, from big N onwards, always makes this true. Right? This little n is always greater than or equal to this big N. Therefore, 1 over little n is always less than or equal to 1 over big N. Yeah? Okay. So, then absolute value of 1 over n minus 0 is less than or equal to absolute value, well, 1 over n minus 0 is just going to be 1 over n, right? And absolute value of 1 over n is just going to be 1 over n. Are you good with that, Lee? Because n is always a positive number, so 1 over n is a positive number. Absolute value of a positive number is just the number itself. So 1 over n minus 0, absolute value, is the same thing as 1 over n is less than or equal to 1 over big N is less than epsilon for all n greater than or equal to big N. So from big N onwards, this whole inequality is always true. 5, therefore, n converges to 0. That's what our definition is. Converges to 0. So that's what our definition of convergence means. An converges to A, or 1 over n converges to 0, if for every epsilon you pick, we just picked an arbitrary epsilon, this is less than epsilon, this is less than epsilon, for all n from some big N onwards. It doesn't matter what this big N is. If you can find a big N that makes this true, the sequence converges. So if epsilon were this, then this big N would work. But this big N would have also worked. We could have used a bigger one. Right? Questions so far? Or should we just do another example?
Can I just think about it for a second?
Sure. maybe one way to help establish intuition for it would be to pick real values real quick and just work it all the way out.
What we just did.
I know, but what I'm saying is, you pick a real value, pick any small number you want, and I'll show the point in the sequence where from that point in the sequence onwards, we're always within your real number of 0.
Okay.
I don't know. Does that sound helpful, or is that just repetitive?
I'm just trying to get used to the way that we're doing the proof. Like I understand the concept. It's like I just want to make sure that if I had to go replicate this, I can at least give it a shot and not totally fail.
Okay, then let's just do another example. So let's prove that this sequence, n over n plus 1, converges to 1. Same way, what do I need to do? I need to show that for any epsilon you choose, I can always find an index big N such that n over n plus 1 minus 1 is less than your epsilon from that big N onwards in the sequence. Right? So,
Isn't it n plus 1 over n converges to 1?
Yeah.
Doesn't matter. They both converge to 1. Right?
One just from the positive.
This is just always barely less than 1, and this is always barely bigger than 1.
Oh.
So, yeah, it still works. So, 1. Let epsilon be any positive real number you want. Doesn't matter. 2. So, our scratch work is remember what we're trying to get. Ultimately, I'm trying to show that n over n plus 1, minus 1, I'm trying to show that this is less than epsilon for all n greater than or equal to some index. So I'm trying to find an index n where this is true. If I can find some big N where this is true, then I'll have proved it. So I need this less than epsilon. Well, this will be less than epsilon when we're going to simplify this expression. So I need absolute value of n over n plus 1 minus 1, which is the same thing as simplifying this. I'm going to times this top and bottom by n plus 1. So I'm going to get n minus n plus 1 all over n plus 1, absolute value. Good with what I did there? N minus n plus 1, this is just equal to 1 over n plus 1. Right? Which is, well, I'll just write it and then translate it. And then this is going to be less than or equal to 1 over 2n. Right? For the natural numbers, if n is 1, they're equal. If n is bigger than 1, then this...
It's greater.
No, it's not greater.
Oh, it's less
Sorry.
than.
So we don't need to do that. We need to make something bigger. Okay, so this is less than or equal to n. There we go. Right? If I make the denominator smaller, I made the whole number bigger, and it's just less than. Which is equal to 1 over n. So, if I can make 1 over n less than epsilon from some index onwards, then this will be less than epsilon from some index onwards, then this will be, then this will be, then this will be. So if I can just make this smaller than epsilon, everything else is going to be smaller than epsilon, right? Because it all changes together. This is the same as this, is the same as this, is less than this, is equal to this. So if this is less than epsilon, then this is less than epsilon, then this is, then this is, and this is. So this is our scratch work that we do to decide to think about what n I'm going to choose. Because I need to choose the n that makes this less than epsilon. So 2, by Archimedean property, there exists some natural number, call it big N, in the natural numbers, such that 1 over big N is less than epsilon. Archimedean property. For any small number you pick, I can find a natural number such that 1 over that natural number is smaller. Then, the absolute value of, what was it? N over N plus 1? N over N plus 1 minus 1 is equal to the absolute value of, we'll skip to 1 over N plus 1 is less than 1 over N is less than or equal to 1 over big N for all N greater than or equal to big N. Right? Because if I make this number bigger than or equal to this number, then this number is less than or equal to this number. Since the denominator is greater than or equal to this denominator, then the whole number is less than or equal to this whole number. And then we already know that this is less than this, and we know that this is equal to this. That was just using the scratch work I did down here.
How do we know that?
How do you know that little n is less than big N?
Yeah, that's exactly what I was going to say.
It's greater than big N.
For all little n greater than or equal to big N.
Yeah.
Oh.
I'm saying that this is only true for these n onward. So if big N is 1,000, then I'm saying this inequality is only true starting at 1,000. 1,000, 1,001, 1,002, 1,003, etc.
So, I don't know, maybe I think I've lost something, but why
That's fine.
do we need to have a big N at all and not just say little n is less than epsilon?
For every n? Because then I couldn't say that 1, 1/2, 1/3, 1/4, 1/5. I couldn't say that this converges to 0. Because let's say I pick a really small number, 0.000001. Is this number within 0.00001 of 0? No. So I'm saying, yeah, this one's not within 0.00001 of 0, but I'm saying eventually in the sequence, we're going to eventually get to some number 1 over 1, 0, 0, 0, 0, 0, doesn't matter. We're eventually going to get to some point in the sequence
But we're never going to get to 0.
we're never going to get to 0, but what I'm saying is,
Closer to 0. So they're always going to be in between that number and 0.
so here's the epsilon that we chose. Pretend I chose this epsilon. This number is not within epsilon of 0. This number is not within epsilon of 0. This number is not within epsilon of 0. But if I continue in this sequence long enough, I'll eventually get to this number. And this number is within epsilon of 0. And every number after this number in the sequence, all infinite of them, are within epsilon of 0. So here's my big N. My big N is 1 million in this case. From 1 million onwards in my sequence, I am within epsilon of 0.
That makes so much sense.
Wonderful!
That
That is what all we're saying here. All we're saying is, look, I need to find some point in the sequence where from that point onwards, we're within epsilon of what we're saying it converges to. That's all we're saying.
Yeah.
It's dense, but once it clicks, it's like you're just saying English. It's like, I understand you. So it's dense until it clicks, and then it finally clicks. So this whole inequality is true from some big N onwards, right? And I chose big N such that 1 over big N is less than epsilon.
Right.
So therefore, N over N plus 1 minus 1 is less than epsilon for all N greater than or equal to big N. From that index onwards, we are always within epsilon of 1. Therefore, this thing converges to 1. It gets as close as you want to 1. There comes a point in the sequence where from that point onwards, we're guaranteed to be within epsilon of 1. And it works for any epsilon you pick. I could have picked a way smaller epsilon. That just means I would have had to go way further in the sequence. Doesn't matter. I can still find the point. And from that point onwards, all infinite terms are going to be within epsilon of the number. Good? So let's go back and read the definition one more time now that we're connecting from examples. And get rid of this. Okay, so our definition. A sequence AN is said to converge to some real number A, provided that for every positive number epsilon, there exists some natural number n such that this inequality is true from that n onwards. Say it one different way. A sequence AN is said to converge to a real number A, provided that for every positive number you pick, I can find an index in the sequence such that from that index onwards, the sequence is within epsilon of A. Is this clicking? Do I need to try and find another way to say it, or do you think we're ready to move on to just proofs?
Was that proof finished?
Yeah. We showed that n over n plus 1 minus 1 is always within, we showed that this is within epsilon of negative 1, or of 1, sorry, from this index onwards.
Oh.
Let me rewrite this.
Right, no, that's the definition of converge over
This is the definition of convergence, but let me rewrite the inequality using something that we did last time. So, if I could rewrite this as 1 minus epsilon is less than n over n plus 1 is less than 1 plus epsilon. N over n plus 1, from this n onwards, is always in between 1 minus epsilon and 1 plus epsilon. So it's always getting closer and closer to 1. You pick smaller and smaller epsilons, you're squishing it closer and closer and closer to 1. Good? Okay. So let's move on to our next proof then. So, next we're going to prove that if you have a sequence that converges to a number, then it only converges to one number. In other words, a sequence can't converge to two numbers. It can't get really close to two numbers. And that should make intuitive sense. Here's intuitively how we're going to think about it. So let's pretend that we have a sequence that gets really close to A, and that gets really close to A prime. Then I'm going to pick some small epsilon. So that epsilon, here's A plus epsilon. Epsilon is only this much distance, so it gives me from here to here, here to here, and here to here, here to here. My sequence cannot, from some point onwards, always be within this and be within this, because they have no overlap. It has to be within one or the other. So it can't be in both. Right? So that's picture of what we're going to do, roughly. Let me draw the picture out a little bit better, actually, because I'm actually going to call things exactly how I show them in this picture. So here's A prime. I'm going to choose epsilon. So that epsilon is less than, let's see, I may call the bigger of the two numbers A prime. Doesn't matter, right? Just, if we have two numbers, one's bigger than the other, call the bigger one A prime. So I'm going to make sure that epsilon is less than A prime minus A over 2. What's A prime minus A over 2? A prime minus A is this distance, divided by 2 is half the distance. So I'm saying epsilon has to be less than half the distance of these. That way, when I do A minus epsilon, we only get out here. Here's A minus epsilon. Here's A plus epsilon. Here's A prime minus epsilon. And here's A prime plus epsilon. So if my epsilon is less than half the distance between these points, then I'm guaranteed that these two have no overlap. This one only goes to here, this one only goes to here, there's no overlap between them. Make sense?
So, quick question. If you had something like, it wouldn't be a sequence because it wouldn't be a function, but you know, like an inverse function where you can have one element that maps to 2 places, right?
Okay.
Would it be possible then to have it converge to 2 points?
If I have something that's not a function.
Yeah, but the same idea. If that makes sense. So like it's not a function, but it's the same idea. It takes a point, maps it, except for this time it maps it to 2 points. Then it could converge to 2 different places, right?
So we'll have a notion of, once we have a continuous function, something like this, we'll have, well, that still isn't getting at your question. Here's a way to answer your question. If there isn't one and only one answer, then we can't have it defined. So I need to do this proof so that when we say the limit of a sequence, it's now defined. It's one and only one number. Otherwise, it's ill-defined. It has to be one and only one thing. Otherwise, you don't have it well-defined.
What do you mean?
So you're saying, is it possible to have some notion of convergence where AN can converge to many things? Yeah, it's possible to have a notion like that. The same way our notion of upper bound, there's many upper bounds. But if I want to have a well-defined number, it needs to be one and only one number.
Right.
So when I want to talk about the limit of a sequence, that now has to be one and only one number. So I can't have a limit go to 2 things.
Right.
Otherwise, limit's not well-defined.
So, well, what I'm saying is will it ever come up? Is it ever going to be useful? Is there any idea of converging to 2 points?
No, convergence is just setting us up for the idea of taking a limit, and a limit's well-defined. Because from here on out, continuity, taking a limit. Differentiation, taking a limit. Integration, taking a limit. So calculus is always taking limits. And the limit's well-defined.
So it might be possible, but it's never going to be.
Well, possible. I mean, it's just how you define something to be.
Right.
Define it however you want,
Right.
and then what it can do, it can do.
Right.
Sure. All right. So here's what our picture is going to be. And then we're going to know that since we're going to do a proof by contradiction, we're going to assume that AN converges to both A and A prime, and so that leads to contradiction. What's the contradiction going to be? It's going to be that there's going to come a point in a sequence where AN is guaranteed to be in here, and AN is guaranteed to be in here. So then I'm going to have AN
It's in 2 places.
is less than A plus epsilon, is less than A prime minus epsilon, is less than AN. And that's my contradiction. AN, which is a contradiction. AN less than AN is going to ultimately be my contradiction. So that's a big picture of how I'm going to go about this. So let's start the proof. 1. Assume, by way of contradiction, that AN converges to A and A prime. 2. Without loss of generality, assume A prime is greater than A. What do we mean by that? We mean if A is bigger than A prime, relabel them. So that now A prime is bigger than A. Doesn't change our proof. Good? Okay. 3. Since AN converges, I need to get my epsilon. Probably should have said that somewhere up here. Let epsilon be less than A prime minus A over 2. So now, if AN converges to A, what do I know? I know that for any epsilon I pick, I'm just picking some epsilon less than that, then the sequence, well, let's write it out and then say it because it's dense. So 4. Since AN converges to a, comma, then there must exist some point in the sequence, some natural number, call it n1, in n, such that an minus a is less than a prime minus a over 2 for all n greater than or equal to n1. So in other words, if I know that an converges to a, then for any positive number I pick, there comes a point in the sequence, we're calling it n1, such that this inequality is true from n1 onwards. Right? Similarly, comma, there exists n2 in n such that the absolute value of an minus a prime is less than a prime minus a over 2 for all n greater than or equal to n2. So since an also converges to a prime, this is true from some index onwards. So this is true from n1 onwards. This is true from n2 onwards. If I let n be the bigger of these two, then both of these are going to be true from n onwards. Does that make sense? In other words, if this is true starting at 100 and this is true starting at 1,000, they're both true if you just start at 1,000. So that's what I'm going to define n to be, the max of those two. 6. Let n be the max of n1 and n2. n1, comma, n2.
Why do we have two different n's?
So I know that an converges to a, and I know that an converges to a prime.
Okay, that makes sense.
Okay, so pick the bigger of those two, and then that n makes both of these true.
Which is true. Right?
Yeah.
Okay.
So then, I'll just say 4, 5, true for all n greater than or equal to n. So in other words, both these inequalities hold from big N onwards. Since big N, we just make it whatever's bigger of those two. Make sense? Oh. I guess I could go plug it in out there. I wonder where I put in this inequality. Let epsilon greater than a halves. I'm going to do some algebra here. This is going to be the same as, let's see how I want to get it. I need to get basically a plus epsilon. Let's mark the middle point here. The point right here, the middle point between these 2 points, is going to be a prime minus a, or plus a, over 2. There we go. That's the middle point between a and, oh, a's right here. A prime, their middle point is just their average. What's the middle of 5 and 7? It's 6. 5 plus 7 divided by 2, 6.
So why did we say a prime minus a?
A prime minus a is this distance. Or sorry, a prime minus a is this distance, the distance between them. Divided by 2 is this distance. This distance is a prime minus a over 2, but this number is their average.
That makes sense.
Does that make sense for everyone? We don't need to draw a picture of that. Okay, So I'm going to use the fact that I defined epsilon to be this way. I'm using this to get my inequality. The inequality I want to get from that is that a plus epsilon is less than a prime plus a over 2 is less than a prime minus epsilon. That's the inequality I need to get. And you can see that from this picture, right? A plus epsilon is less than the midpoint is less than this. So, let's see. I'm going to take this, I'm going to add a to both sides. So that's going to give me a plus epsilon is less than I don't know, can I do all this in my head?
Yeah.
So when I add a to this, I'm going to get a over 2 plus a prime over 2.
Yeah.
Let's write it out up here real quick. I'm just writing out space in my proof, which is why I'm doing this. So I'm going to do a plus a prime minus a over 2. Well, that's the same thing as a plus, just split this into two fractions and it becomes obvious. A prime over 2 minus a over 2. Okay, a minus a over 2 leaves me a over 2. A minus half of a leaves me half of a. So then we have a over 2 plus a prime over 2. When we add a to both sides of this, going from here to here, which is what the midpoint is. So that's why we did that. And let's see. But we can also write this as a prime minus a prime minus a over 2. Okay. So let's make that one make sense.
Okay.
A prime minus a over 2 is the same thing as a prime minus, let's just split this into two fractions, a prime over 2 minus a over 2 is equal to a prime over 2 or a prime minus a prime over 2 leaves us a prime over 2, and then minus negative a2 is plus a over 2. So this is just a different way of rewriting the same fraction. Right? And now I know that this number is bigger than epsilon. So this is going to be less than a prime minus epsilon. Because if a prime minus this is bigger than this, then when I'm subtracting a smaller number, we made it bigger. I made the number I'm subtracting smaller, therefore the number's bigger. Because epsilon is less than this. This is all just a bunch of work to make sure that we get a plus epsilon is less than a prime minus epsilon. That's all I'm using all this to do. I'm basically saying, since a prime is bigger than a, and since I defined epsilon to be less than this distance, and exactly what our picture tells us is true right out the door, namely that a plus epsilon is less than a minus epsilon, I'm just now doing the algebra to show that's true. And all I'm showing is that a plus epsilon is less than a minus epsilon. That's the whole motivation for doing all that. Good?
Algebra is a bit tricky, but yeah.
Yeah, you just need to know that I need to rewrite this number in a way that makes it obvious that it's bigger than this number and less than this number. And because this is the number acting as our middleman. I showed that this is less than this is less than this by rewriting this number two different ways. And in fact, I probably shouldn't have even written it this way to begin with. We should have done is less than a, the way we had it the first time, a plus a prime minus a over 2 is equal to a prime minus, and that probably helps motivate it better. I'm saying a plus half their distance is the same thing as a prime minus half their distance. That's the midpoint, and that probably helps you see it better.
Yeah, that is.
So this number is bigger than epsilon. So when I add something bigger than epsilon, I can only make it bigger. And then, once again, this number is bigger than epsilon. So if I subtract something smaller than this number, I can only make it bigger. To make this number bigger than this number, I subtracted a smaller number. To make this number bigger than this number, I added a bigger number. And then showing that this is equal to this is just algebra. Is that helping? Good? Ready to continue? Okay. So, there's all that algebra. 7. Then, so since I know that 4 and 5 are true from big N onwards, then I know that, let's see, start with this one. This is less than epsilon. Why did I do that? Epsilon and epsilon. Sorry. I don't know why I did that. Epsilon. Exactly what we do in our definition. So I know that this is less than epsilon from some big N onwards. I know that this is less than epsilon from some big N onwards. So I'm going to use that to construct this contradiction. Is exactly where I'm going. So then I know, using number 4, rewriting this inequality right here, that gives me negative epsilon is less than an minus a is less than epsilon, which gives me plus a to both sides of this side of the inequality. We don't care about what's over here. But if I plus a to both sides of this inequality, that gives me an is less than a plus epsilon. Are you good with that? Taking this half of the inequality, add a to both sides. So that gave me this. Now I'm going to construct this. And then my algebra up here is going to give me the middle part. So my algebra gives me the middle part. And then the fact that an converges to a is giving me this part. And the fact that an converges to a prime is going to give me this part. So,
I think you lost me.
am I just explaining so much at Lucia instead of just finishing it?
No?
No? Okay. You understand the contradiction that we're after.
Yeah.
So I'm going to get that an is less than a plus epsilon, and an is greater than a prime minus epsilon. Therefore, an is less than an. Contradiction. Now, how do I know that a plus epsilon is less than a prime minus epsilon?
You just did, yeah.
That's coming from just our definition for what epsilon is. That's just the algebra we did here. A plus epsilon is less than a minus epsilon. Okay, so that gives me the middle part of this inequality, right?
Right.
I know that an converges to a, which is going to give me this part of the inequality. So, since an converges to a, then an minus a is less than epsilon. Right?
Because of the definition.
By definition of convergence. So an minus a is less than epsilon. Well, rewriting this, that's the same thing as this.
Okay.
And then looking at just this part of the inequality, add a to both sides, gives you this. So there's my an's less than a plus epsilon. Similarly, from the fact that an converges to a prime, that's number 5, that gives us this inequality. So rewriting this, that gives me negative epsilon is less than an minus a prime is less than epsilon. In this case, we just care about what's over here, and we're going to add a prime to both sides. So looking at just this part of the inequality, add a prime to both sides, and we get a prime minus epsilon is less than an. Combine all three inequalities. Therefore, we have this inequality gave me an is less than a plus epsilon. This inequality gave me a plus epsilon is less than a prime minus epsilon. Less than a prime minus epsilon. And then this inequality gave me a prime minus epsilon is less than an. And this is only true from some index onwards. But there's our contradiction, right? I can't have an less than an from some index onwards. Doesn't make sense. Good? Dense proof, a lot going on. Rewatch it 6 times. Not for you, I just want views.
Okay.
So there we go, that's that proof. Any questions about this proof before I erase the picture? You getting tired? Tired of analysis at this time? Doesn't make sense. Alright. I'm good to start erasing?
Yes.
I'm just erasing like the picture stuff so that we can continue with proofs. I probably shouldn't have written these out. I probably should have just made a list of what we were going to prove. I think that works better.
Gives you more space to work with?
Did we already prove this one?
No.
Oh, no, because we need to talk about the definition. Okay, so we proved if a sequence converges, then it converges to one and only one number. So now we can define that number. And we're going to call that number the limit. We do proofs like this all the time. Remember when we want to define the additive inverse. Before I could define the additive inverse, I had to prove that there was one and only one. The axioms told me that there was at least one. Then I needed to prove that there was only one and one. There was one and only one. So it's a common thing that we do to help us define a particular number. So now we know what the limit of an is. It's a. So if an converges to a, then the limit of an is a. And from here on out, we'll just talk about the limit of an, and we'll stop saying an converges to a. Just say the limit of an.
Why is that useful?
Because now it's a particular number. The same way that we don't say let y such that x plus y is equal to 0. We just say negative x. We now have a defined number. So instead of a being the number that an converges to, we just talk about the limit of an. Okay, so let's do this proof. I'm proving that this converges to 3, obviously. How are we going to start every proof? What's the first thing I write?
Let something.
Let, solid. Let. Alright, we've got that far.
You let epsilon in R.
Let epsilon be some positive number. So let epsilon in R plus. Pick any positive number you want. I'm showing that this sequence eventually gets within epsilon of 3. That's what I'm saying. It converges to 3. This gets arbitrarily close to 3. For any epsilon you pick, this eventually gets within epsilon of 3. Which you can intuitively think, right? For really big n's, this approaches 0, this approaches 0, this approaches 3. Yeah, it gets really close to 3. Okay. 2. So we need to find the n. Now we always go to the side and we do some scratch work to help us think. And so I need 2 over n squared plus 4n plus 3. I need to get this all less than, and then minus 3, right? I need to show that the sequence minus what it converges to is less than epsilon.
Right. And
right? When it converges, the sequence minus what it converges to, less than epsilon.
That makes sense.
So I need to get the sequence minus what it converges to, less than epsilon. Well, first off, this is just equal to 2 over n squared plus 4 over n. Right? And then, let's let's see, how do I want to do this? Times this top and bottom by n, I guess. So this is just equal to 2 plus 4n over n squared.
Okay.
The absolute, we're only dealing with natural numbers, so the absolute value is not going to change anything. So I may get rid of the absolute value and simplify at the same time. This is not equal to. This is now going to be less than 2 over n squared. So if I don't add 4n, I definitely made the number smaller. Right?
No, we made the number bigger. Right?
Oh,
Because you're
what am I
saying
doing?
backwards.
I'm cheating.
Yeah.
So we don't want to do that.
No.
Here's what we want to do. Okay, this is less than 2n plus 4n over n squared. Okay, we can do that one. That for sure made it bigger, right?
Yeah.
Because I just multiplied 2 by n. And then the n's go out, so then this is equal to 2 plus 4 is just 6 over n. Okay, and that's simple enough that we can work with it.
Is that less than or less than or equal to? Because what if n is 1?
Good catch. Less than or equal to.
How can you just times 2 by n?
I'm saying if I take 2 and I multiplied it by n, I only made it bigger, because n's natural numbers. So n is either 1 or 2 or 3 or 4. All I'm trying to do is to get something really simple that I know that this whole mess is for sure less than.
Okay.
It doesn't matter what it is. I could just as easily make this over n cubed. Wait,
No.
that makes it smaller.
6 cubed.
I could have just as easily made it over, 6,000 here, and we still would have been fine. I just need to find some expression that's easy to work with, that this is for sure less than. Because then if I can make this expression less than epsilon, then I for sure make this less than epsilon, and we're good. So when will I know that 6n is less than epsilon? So I need to make this less than epsilon. I know that 6n will be less than epsilon when 1 over n is less than epsilon over 6.
That's just multiplying both sides by 1/6, right? Essentially.
Yeah, multiply both sides by 1/6. So if this is true, then this is true, then epsilon greater than this is true. You follow all that? There's all our messy scratch work. Now we come back to our proof. So by Archimedean property, there exists some natural number n such that 1 over n is less than epsilon over 6, right? Epsilon over 6 is just a positive number. The Archimedean property tells me that for any positive number you pick, epsilon over 6 is a positive number, I can find a natural number big N such that 1 over n is less than epsilon over 6. And notice that this is the same thing as 6 over big N less than epsilon. Right?
So little n and big N are two different things?
Well, we'll come back to, we'll use the little n now here in a sec. We'll use it in my next line, but just, you understand how everything here is true so far, right?
Sure.
Okay. 3. Then, absolute value of 2 over n squared plus 4 over n plus 3 minus 3 is less than or equal to 6 over little n is less than or equal to 6 over big N is less than epsilon, but this is only true when little n is bigger than big N. So this is true for all little n greater than or equal to big N. That's where we time the little n. Because the little n is always going to be in these proofs, all the natural numbers greater than or equal to big N. That's what little n will always represent in these proofs. Good? And finally, therefore, break?
This is getting a little bit. I'm just trying to follow. I feel like I need a minute to think about it. It's like,
How does
part
that
of it's
equal
notation, like,
Say that one more time.
How does that equal 3? Oh.
We showed that this converges to 3.
Mm-hmm.
So the limit of this is 3.
Oh.
We're getting it?
I don't know why the part that I'm having a hard time with is algebra, seeing how algebra is like the one thing that I should not be having a hard time with. But okay.
Alright. Let's do one more example and then we'll do a break. So let's show that something does not converge. So I may show that -1 to the n does not converge, and it's going to be pretty similar to the way that we did this proof. We're going to pick an epsilon so small, we know that this sequence alternates between what?
-1 and 1.
-1 and 1. So if we pick an epsilon so small that it can't contain both -1 and 1, then it definitely can't contain all the terms in the sequence from some index onwards. Does that make sense? So let's show that this doesn't converge. So to show that something converges, I need to show that for any epsilon you pick, I can find an index in the sequence such that from that index onwards, we get within epsilon of, I guess we didn't write it that way over here. To show that something converges, I need to show that for any positive number you pick, I can find an index n such that this is true from that index onwards. That's to show it converges. How do I show it doesn't converge? We need to do the negation of this. You remember how to negate quantifiers? I need to show that there exists a positive number such that for any index onwards, this is not true.
Can't you just come up with a counterexample?
Not quite. I mean, that's what we're doing. Our counterexample is going to be an epsilon. But how do I show it's a counterexample? I need to show that whatever epsilon, that counterexample, epsilon, so in our case we're going to pick something like 1/2. I need to show that for 1/2, there is no index in the sequence such that this is true from that index onwards.
Yeah, it's basically a counterexample.
It's a counterexample, yes, but it's not as simple as like counterexamples in discrete math where it's just pulling up one number. In other words, proving something doesn't converge is basically as hard as proving it does converge. It's not magically easier like other counterexamples typically are. Is this right, good? Yeah. So let's do the proof. 1. Let epsilon equal 1/2. 2. Then we're going to show that there can't be any index such that this sequence is always within 1/2. There can't be any number such that this sequence is always within 1/2 of that number.
So you're saying that epsilon doesn't exist?
I'm saying that this sequence doesn't converge because I can find an epsilon such that this sequence is not within epsilon of any number. Any number you pick, this sequence is not going to be within epsilon of that number. So it doesn't converge to any number because it never gets within epsilon of any number. Do you see what I'm saying?
I see what you're saying.
Because what is this sequence? This sequence is -1, 1, -1, 1. And it just keeps doing that over and over again.
Oh,
Right?
yeah.
So keeps going, doesn't matter how far you go, it's still just -1, 1, -1, 1, keeps going, keeps
I
going.
feel like maybe we should, like, an easier way to prove it, I feel like, would be maybe the two possible converges, which is 1 and -1, and show that neither one works.
If it converges, it only converges to 1 or -1. That appeals to our intuition, but we can't say that.
Not necessarily. I mean, if it does converge, then it would converge to just those two, but then we show that it can't converge to either.
Right, so what you're saying intuitively makes perfect sense. So our intuition is, since this is only negative ones and ones, if it converges, it has to be either to 1 or negative 1. Right? And while that makes perfect sense, we don't have a way to prove that.
In fact,
There's
we
no
just proved that it wasn't.
formalized way that we have to capture that notion of a sequence. If it has a finite number of terms that it alternates between, it has to eventually just converge to one of those terms.
I mean, the sequence itself proves that it doesn't converge.
It's very appealing to our intuition that this does not converge.
So why do we have to prove it?
Well, we don't have to.
Okay, let's do it.
Alright. So let's prove that this does not converge. So let's assume by way of contradiction that it does converge. Assume by way of contradiction that there exists some A such that the limit of -1 to the n is equal to A. Let's assume that this thing converges, or in other words, that it has a limit. Right? Alright. 3. Then A minus 1/2 is going to be less than A is going to be less than A plus 1/2 for all n. Well, I need to say that there exists some n such that this is true, sorry. So if this does converge to A, 3, then there exists some big N in N. There exists some natural number such that AN minus A is less than 1/2 for all n greater than or equal to that natural number. And then do some algebra on this inequality to help us think about it. So then, just rewriting this inequality, let's see what we're going to get. We're going to get A minus 1/2 is less than AN is less than A plus 1/2 for all n greater than or equal to n. Right? Same thing. This is just another way of rewriting this.
Oh, yeah.
Or in other words, before I say that, this is also the same thing as, maybe this is the best way to say that. AN is in the interval A minus 1/2, A plus 1/2 for all n greater than or equal to n. Same thing. Now notice, what's the length of this interval?
1.
1. So we know that intervals of length 1 can contain at most how many integers?
1.
1. Remember, for any real number c to c plus 1, we're guaranteed contains one and only one integer. But the point is, any interval this big contains at most one integer. So any interval this big contains at most one integer, because this is smaller than this. So this is an interval smaller than this interval. Right? Barely smaller, but smaller. So it contains at most one integer. So this is true from big N onwards. Now big N is either going to be a positive or a negative number. Do you see how what I'm going to say now? Now I'm going to say, doesn't matter what big N is, from big N onwards, you're going to make both 1 and -1 in here, which isn't possible. Right? If AN converges to A, then that means that there exists some index in the sequence such that every term in this sequence from big N onwards satisfies this inequality.
Why are we using AN instead of -1 at the end?
Oh, sorry. Just notation. The same way that we would use f of x instead of rewriting the function.
Alright. This makes more sense to me.
So yeah, we can replace all these a to the n's with the actual sequence, and it's still the same thing. Good? Didn't change anything?
They both work, I was just saying that.
Okay.
Made more sense.
So -1 to the n has to be in this interval for all n greater than or equal to n. Right? If n is odd, then -1 to the n is equal to -1, and -1 to the n plus 1 is equal to 1, right?
Okay.
Making 1 and -1 in a minus 1/2, a plus 1/2. So there's our contradiction in that case. And then if n is even, we're going to get the same thing.
Well, yeah, that is the same thing. You just say n plus 1
n
is
is even, same, right? One of them's 1, the next one's 0. They're both going to be in there. So we'll get a contradiction. 7, therefore, it doesn't converge. -1 to the n doesn't converge. Or it doesn't have a limit, however you want to say it. Does that make sense? Any questions there?
I mean, yeah, it makes sense. I have no idea how I'm going to go home and make a proof like that, though. Like, we're going to go get a different one, setting, prove that this
So,
sequence...
here is my strong recommendation for this, even though you won't do it. You go home, you restart the lecture. Before I do an example problem, you pause. You try to do it yourself. Then, you watch me do it to make sure you did it right. Chances are the first one you're going to get stuck.
Yeah.
I don't know where you're going to get stuck. You probably can't predict where you're going to get stuck. But somewhere along the way, when you go to sit down to it, you're going to get stuck.
Line 2.
So then you do that, reproduce it yourself, and then when it comes to the next one, you probably have a pretty good chance. Now, I'm not necessarily saying go home and try and reprove the theorems. This one's a little bit more involved. But you should be able to reproduce this. You should be able to reproduce this. You might get stuck in some of the... You might get stuck a little bit in this one, but you should overall understand how this is working fine. You should be able to reproduce this, no problem. Once you can produce one of these limit proofs, you can kind of do all of them. After that, it's just a little bit of algebra figuring out how to do it.
Well, first you have to understand what the limit is. And in these ones, it's easy to see, but it's not always going to be easy to see, is it?
Well, there may come points where it's hard to see, but the proof of these is the difficult part. It's not figuring out what it converges to, it's proving that it converges to that thing. So figuring out what it converges to is kind of trivial relative to the proof itself. And then the algebra, the whole trick to the problem is the scratch work that we do to the side. Is figuring out, I need to just show that this is less than or equal to this thing. Going from this to this is the hard part of these proofs. Should be the hard part of these proofs. Once you get used to them. And that's really not that hard.
Right. That's really not that hard.
So once you get a feel for the proofs, then this becomes the hard part of the proof. Not figuring out what it converges to, but that manipulation. Once you get a hang for it. So in other words, when I go to do one of these proofs, this is the only hard part for me. Everything else is just boilerplate.
basically like an inductive proof.
Right, and even for some big thing you're like, I can't figure out what that converges to, well, go get a calculator, plug in a billion. That will probably give you a good idea.
Right.
But usually you can tell. Okay, so yeah, let's go on break for a bit. Come back when you're feeling awake.
I'm awake this year.
I know, Emma's over there struggling. She's you from last year.
Hey, last year was hard, okay?
I don't want to hear your sob stories.
I'm so tired.
It's not.
I am so tired.
Not junior classes, it's like college classes.
Yeah, you've got a full plate. A little crazy. Okay. Set that up. Oh, that's up on the right hand side, by the way. You can ignore that was more on logic last night. Not logic.
Basically logic.
Probability. Which Estonia's not taken. How's that?
It is sad.
Yeah, we had a big conversation about it last night. So if you want to hear about it, you'll have to go watch the lecture.
How'd it go?
And the conversation won't make sense unless you pay attention to the lecture, so make sure you take notes. Okay. So I think this time I'll just, we might need to reference the definition of convergence again, but I don't think we'll reference these proofs. And we already know the definition of the limit, that's simple enough to understand. Alright, you ready to continue? Okay. 6 proofs to get through, then we're done. That should be easy.
I mean, it's only 10.
Yeah, well, we'll see. Okay, so the next proof is called the comparison lemma. And here's big picture what we're saying. We're saying if I know that AN converges to A, so let's assume I know AN converges to A, and if I can set it up so that BM minus B is always less than or equal to AM minus A times some constant C, if I know that this inequality is true for all n greater than or equal to n1, then I know Bn converges to B. So it's a way that we show one sequence converges knowing that another sequence converges without having to do all the work again. So in other words, we already went through all the effort of proving that 1 over n converges to what? 0. Well, since I know that 1 over 2n minus 0 is always less than or equal to 1 times 1 over n minus 0, since I have a sequence, 1 over n, that I know converges to this, and since I can get this is always less than or equal to this from some index onwards, times a constant, then I know that this converges to this. So maybe it's easier to show that this inequality is true from some index onwards than showing that something converges directly. See what I'm saying? So you're using the fact that you know something converges, namely A of n, to show that B of n converges to B.
Could your constant also be 1/2?
Yes.
Then why is there even a point in the constant? Because just taking it away, the inequality still holds.
So maybe we were trying to do it this way. Maybe I knew that 1 over 2n converged, and I want to show that 1 over n converged.
Right.
So then I only know that 1 over n minus 0 is less than or equal to, let's see, oh maybe that doesn't work. Let's keep it, I know that 1 over n converges, and then just set up a scenario. So I know 1 over n converges to 0. Oh, now let's say I wanted to prove that 10 over n converges to 0. Well, this inequality is only true if I multiply this by a 10.
So you can just arbitrarily choose.
So this needs to be less than or equal to this, or sorry, this needs to be less than or equal to this with any constant factor. Make sense? Oh, sorry.
You can just choose any number you want to be the constant.
Yeah, as long as it's within a constant. Look, what we're saying is, we know that this gets arbitrary close to 0. Multiply 0 by a constant, you're still getting arbitrary close to 0. So this gets arbitrary close to 0. So this converges to this. Right? Let's see where I have it written. I know this gets closer and closer to 0. Something getting closer and closer to 0 times a constant is still getting closer and closer to 0. So this gets closer and closer to 0, therefore converges.
Because it's less than or equal to that.
Yeah. So taking something that converges to 0, taking 0, multiplying it by a constant doesn't change anything. It's still 0. Right? In other words, if I know that 1 over n gets closer and closer to 0, take 1 over n and multiply it by as big of a number as you can think of. Doesn't matter. That thing still gets closer and closer to 0. Go crazy with it. Right?
Right.
You seeing it? Okay. So that's essentially what we're saying. So let's prove it. I'm not going to bother writing the proof part. I'm just going to start with the lat and the antecedent. And let's find the same place in my notes. In case I need to reference it. Let's just say let all the stuff. Let an be a sequence such that the limit of an is equal to a, comma, and assume that there exists n1 in the natural numbers and c in the reals such that our inequality holds. Such that bn minus b is less than or equal to c times an minus a. So setting up the antecedent of the theorem. Now what do we need to prove? We need to prove that bn converges to b. That's what we're trying to show. Right? I'm using the fact that I know that this is true. Oh, sorry. For all n greater than or equal to that n. So I'm using the fact that I know that this inequality is true from some index onwards, and that an converges to a to show that bn converges to b. You understand my given information? Not assuming anything weird up there?
I feel like it would be bn converges to a.
I'm going to prove that bn converges to b, or in other words, that bn minus b gets as small as you want.
Don't they converge to the same thing?
No, an converges to a, bn converges to b. Those could be drastically different things.
In all the examples that you showed, weren't they all 0?
I hope not. In this case, we showed that an converges to 1.
No, that's not. Just like barely when you wrote that. You said if we know that an converges to 0,
No,
then
sorry.
we can show that bn converges to 0.
I said that wrong. If an converges to a, then the difference between an and a gets really, really close to 0. So I know that n plus 1 over n converges to what? 1. Right? So when I minus 1 from it, and I plug in really, really big n's, then this difference gets really, really close to 0. So in other words, plug in a big number like 10,000. So then I get 10,001 over 10,000 minus 1 is equal to 1 over 10,000. And as I plug in bigger and bigger n's, this difference gets closer and closer to 0. Make sense? So that's what I'm saying here. So I know that an converges to a, so this difference gets really, really close to 0 for big n's. And I know that this inequality is true from some big N onwards for some constant c. I don't know what c is, it's just some constant though. I know that an converges to a, and I know that this inequality is true from big N onwards, from n1 onwards. And I'm going to use that to prove, okay, then bn converges to b. That's what I'm trying to prove.
Could we see an example where this inequality holds and bn converges to a different number than an?
Sure. So we might use it to show that, let's see. I mean, it's going to feel really contrived now, but let's look at the sequence 1 over n plus 1. And what does that converge to? Minus 1. And we'll get that less than or equal to some constant, doesn't matter, 10 times 1 over n. Minus 0, sorry. So here it is, this converges to 0, this converges to 1. Now that feels really contrived, like you would use the same thing twice, but it doesn't matter.
What's the point of 10 then? Like why is it even?
It's just some constant.
Why is it useful?
Okay, I'll just put c here.
Well, not why is c?
If I know that this converges to this, okay, and I know that this inequality is true for some c from some index onwards, then I know that this converges to this. You know that in this case the c could just be 1 and n could start at 1, and we're good. That happens to be true in this case.
If it just gets closer to 0 anyway, why does the c even matter?
Because when I'm trying to show that the inequality holds, the c could be useful, like the example I had last time. Like, I want to use the fact that I know 1 over n converges to 0. I want to use the fact that I know this to prove something like 10 over n converges to 0. So I want to show that this converges to 0. I know this converges to 0. There's two ways I could do it. I could work this from scratch and show it converges to 0. Or I could say, hey, look, this is less than or equal to 10 times this for all n greater than or equal to, in this case, 1. Therefore, by the comparison lemma, this converges to this. Now, this is a way stupid, oversimplified example, but it's an example. There's going to come points where this becomes very, very useful. Where showing this is way easier than trying to deal with some sequence that's hard for it to converge. Like, if you know some trig, you know dealing with sine and cosine kind of hard, but you always know that they're between 1 and negative 1. And so it might be easier to just work with 1 and negative 1 than try and deal with a sine wave or a cosine wave that keeps alternating, something like that. I don't know. I mean, we'll definitely see it in action, and we'll see how it is useful directly. But does the information I'm given and what I'm trying to prove make sense? So what am I trying to prove?
That Bn converges to B.
Exactly. Trying to show Bn converges to B. Given all that information, show Bn converges to B. Okay, so how do I show it converges? You know the first word.
Let.
Assume.
Let epsilon and r.
Let epsilon be a positive real number. Let epsilon be any positive real number, doesn't matter. We need to show that this is less than epsilon from some index onwards. That's how we show it converges to B. Using all that given information. So let's see. Let epsilon be some positive number. Oh, and I just made note because that's such a mess. And note that we need to find big N in N such that Bn minus B is less than epsilon for all n greater than or equal to n. Right? Just make it very clear what exactly we're trying to do. I'm trying to show that this converges, which means I need to find some natural number n such that Bn is always within epsilon of B from that index onwards. And we're done. Okay? Okay. It feels like I'm just repeating myself good.
So basically having that inequality is just going to make it a little bit easier.
Yeah, down the road.
Right.
So it's going to be annoying to prove it, but then once we have that tool, then we no longer have to work with the definition of the convergence directly. Well, there's times where it will be useful, but there's times where it will be easier not to have to take the limit of the sequence directly, but just compare it to another sequence that is easier to take the limit of. It's kind of like when we're doing these proofs to begin with, I say dealing with, some expression is kind of complex, I don't want to deal with that, but that's really nice to work with. And if something's true for this, then it's definitely true for this. It's going to be a similar type of thinking where I need to show something about Bn, which is real hard to work with, but An's real nice to work with. So I just want to show An converges, and then Bn's always less than or equal to An within a constant factor. Okay, so let's continue. So A, we know that the limit of An equals A. What does that mean? That means for any epsilon we pick, we can find an index where An's always within A of epsilon. So since the limit of An is equal to A, comma, then there exists some n2 into natural numbers, some index, such that the absolute value of an minus a is less than epsilon over c for all n greater than or equal to n2. Basically, we're saying an minus a is going to be less than epsilon over c. We're going to use this to say that side work to see what we're thinking. We need to get c times an minus a is less than epsilon, because then we have bn minus b is less than or equal to this. So I'm getting this is less than epsilon over c. Why? Because that's going to give me this part right here.
Okay, but is that...
And then I'm going to use the fact that the inequality holds to give me this part. And there, that way I have bn minus b is less than epsilon for all n greater than or equal to some index.
Right, that makes sense. But how can we just divide epsilon by c?
Epsilon is just a positive number. C is just a positive. I didn't say C a positive number. Sorry. C has to be a positive number. Because we don't want, and this is absolute value, so this has to be positive, this has to be positive. I can't take a positive, multiply it by a negative, and have it greater than or equal to a positive, right? So it still works how I said it, but just make sure that we understand C is a positive number, right? So I know since an converges to a, then for any positive number I pick, epsilon over c, that's a positive number. Right?
Okay.
So epsilon over c, that's just a positive number. So I know that this is less than that positive number as long as I go far enough in the sequence. As long as I go clear down to n2, wherever that is, and I start there, then from that point onwards, an minus a is always less than epsilon over c. Good? Which is going to give me c times an minus a is less than epsilon, once again for all n greater than or equal to n2. But I know, maybe I'll write this as a line. Note that bn minus b is less than or equal to c times an minus a for all n greater than or equal to n1. So this inequality is true from n2 onwards. This inequality is true from n1 onwards.
Because we just assumed that to be
Yeah, that was part of our assumption. We said if this inequality is true from some index onwards, and an converges to a, then bn converges to b.
Oh, and now we find the max of n1 then.
Exactly. So if I let n equal the max of n1, comma, n2. So if this inequality is true from n1 onwards, and this inequality is true from n2 onwards, then they're both true from whatever's bigger out of these two onwards, right? In other words, if n2 is 1,000 and n1's 1,000,000, so I know that this is true from 1,000 onwards and this is true from 1,000,000 onwards, then both of them are true from 1,000,000 onwards. That make sense? Wonderful. Okay, 6. Then bn minus b is less than or equal to c times an minus a is less than epsilon for all n greater than or equal to n. We're done. Maybe put one more line. Therefore, the limit of bn is equal to b. And then we'll say we're done. Right? We just barely show that we can find an index n such that bn minus b is less than epsilon from that index onwards. That's what it means for bn to converge to b. just need to look at for a sec, or? Are we good to race and move on? No. What's holding you up?
I don't know, I need a minute to,
Okay.
I mean, every step that you take makes sense, but
I know.
it doesn't feel good.
You feel like, yeah, I can go an inch each time. Then you're like, okay, we went a mile, see? Like, no, I can't see that far back.
Yeah, I just need a sec to.
No, that's fine. What?
I don't understand how we can take that inequality and prove that inequality using that inequality.
We didn't prove the inequality.
Right, but the inequality says Bn converges to B, and that's exactly what we're proving.
No, the inequality says b(on minus b), whatever this number is, if this difference is less than or equal to this difference from some index onwards with a constant factor, and this difference tends towards 0, then this difference tends towards 0. That's what we were showing. Tends towards 0 is the same thing as this, gets closer and closer to this, is the same thing as this converges to this.
So if An converges to A, and that gets closer and closer to 1, then Bn minus B would have to be getting closer and closer to 1.
If an converges to 1, then a is 1. If an converges to a, their difference is always 0,
Okay.
or getting closer and closer to 0. So no matter what sequence this is,
It's always
and no matter what it converges to, its difference is always getting closer and closer to 0.
Okay.
Does that make
So
sense?
something less than that would also be getting close to 0.
Yeah, so something less than or equal to that, within a constant factor, will also get closer and closer to 0. So, using our calculus language now, we say, if an converges to a, and if this inequality is true from some index onwards, then bn converges to b. So we were using the fact that this inequality is true from some index onwards, and that an converges to a, to prove that bn converges to b.
Okay. How do we know that that inequality is true?
We're given that it is true from some index onwards.
So we're giving it where?
It's part of the proof. The proof is that if an converges to a, and if there exists c in n1 such that this inequality is true from some n1 onwards, if we have those, so that's what's given, then all we're showing is that bn converges to b. So we're given a lot of information to show bn converges to b.
Okay, that makes sense.
And so we just use the fact that an converges to a to give us this inequality, and then we use the fact that this inequality holds to get this part of the inequality, which gives us the whole thing. Good to move on? All right.
This feels like when you taught us the beginning probability, and we did random variables, and it was like so much was thrown at you all at once in the way of notation that it was just hard to keep up because we just barely got introduced to sequences, and now we have to remember, oh yeah, that's a sequence, and oh, that's a series, oh, that's...
Yeah. But now you know what a random variable is, right?
Yeah, no, it's not hard.
What's a random variable?
It's not random, but it's not a variable.
It's just a function that spits out a real number.
Yeah.
That's a random variable. That's all it is. Easy peasy. All right.
Then you're trying to learn expected value, and I was like, wait, I don't even know what that symbol means.
So next, now notice limit now is just a unary operation, right? A limit, what does it do? It takes a sequence and it spits out a real number. Its input is a sequence, its output is a real number. That's what it does. So it's just an operation we can apply to a sequence of numbers. And it spits out a real number. So now we're going to prove some really nice theorems about limits. First thing we're going to prove is that the limit of a sum of sequences is equal to a sum of their limits. So in other words, if I can take some sequence and split it up into two sequences, such that I know the limit of the first and the second, then I know the limit when I put them back together and add them back together. And that's one way to think about that. The limit of the sum of sequences is equal to the limit of the individual sequences. So in other words, let's do a hard example. The limit of n plus 1 over n is just equal to the limit of n over n, that was a very good one, plus the limit of 1 over n, right? Because I can split this up into n over n plus 1 over n, right? N over n is just 1, so this is just a sequence 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. So what's the limit of 1? What does this sequence converge to?
Nothing.
What does it keep getting closer and closer to?
It doesn't converge.
It converges to 1.
This doesn't even make sense.
For any epsilon you pick, this sequence is always within epsilon of 1.
Yeah, it is.
Because it's always 1, right? It's the most trivial limit. We probably should have done that as a proof.
Yeah.
Prove that the limit of a constant is just equal to the constant.
Wow,
Yeah.
that would have been helpful.
So, well, we can do it really quick. Let epsilon greater than 0 or be a positive real number. I'll probably sometimes just write greater than 0. Then, c minus c equal to 0 is less than epsilon for all n greater than or equal to 1. You can just start at 1. It's always true. You don't have to go find a point in the sequence where it starts being true. It's true right at the beginning. Because c minus c is just 0. There we go. You just better prove that the limit of a constant is just a constant.
Why is that C and that N?
Oh, sorry. We can do this. I don't know what you want to call the sequence. AN. We'll call the sequence AN, and it converges to C. But the sequence AN is just C, C, C over and over again. It's just a constant sequence. Let's go back. Let AN equal C. It's just a constant sequence. Good? Now we're going to prove it converges to C. Notice that AN minus C, absolute value, this difference is always just 0, which is always less than epsilon for any epsilon you pick, starting at 1. Here's your big N. From 1 onwards, this is true. So I found an index, namely 1, such that AN minus A is less than epsilon. Starting at 1, going onwards. Okay. Keep picking up the bad eraser. I think it's just because it's easier to grab. Alright. So, I think you understand what we're proving. The limit of a sum is the sum of the limits, is the way that people often say it. The limit of a sum is the sum of the limits. So 1. Let AN and BN be sequences such that the limit of we have two sequences that converge, they have limits. We're going to show that the limit of their sum is equal to the sum of their limits. Good? So let epsilon greater than 0 or be a positive real number. And note that we need to find n in the natural numbers such that an plus bn minus a plus b is less than epsilon for all n greater than or equal to that index. That's what we're trying to show. I'm trying to show that an plus bn converges to a plus b. I'm trying to show that an plus bn, its limit, is a plus b. Notice that the limit of an is just a, and the limit of bn is just b. So I'm trying to show that the limit of an plus bn is equal to a plus b. You understand that's what I'm trying to show?
Mm-hmm.
Okay, so this is what I'm trying to prove from here on out. And if I can prove this, then we're done. Good? Alright, so then an plus bn minus a plus b, I can rewrite this as an minus a plus bn minus b. You good with that step? Just basic algebra. Negative a, group it with the an. Negative b, group it with the bn.
Okay.
You see it?
Yes.
Huh?
Yes.
Okay. So then this is less than or equal to an minus a plus bn minus b. Whoa, how did I do that?
It's the triangle property.
Triangle inequality, right? The sum of two things is less than or equal to the sum of their absolute values. Now notice that I know that an converges to a and bn converges. That's supposed to be a minus sign. Sorry. Did I do it? No, I did it right there. I know that an converges to a, therefore I can make this less than epsilon from some index onwards. And I know that bn converges to b, therefore I can make this less than epsilon. Not only epsilon, any positive number. I'll just say it rather than trying to explain them, right? For since the limit of an is equal to a comma, then there exists some index, we'll call it n1, in n such that an minus a is less than epsilon over 2 for all n greater than or equal to n1. And then I'm going to say the exact same thing except for with bn and with n2. So I'm also going to say same thing since blah 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 limit of bn is equal to b, there exists n2 in n such that the absolute value of bn minus b is less than epsilon halves for all n greater than or equal to n2. We're going to make n the max of n1 and n2 so that both of those are true. Let n equal the max of n1 and n2. Then the absolute value of an plus bn minus a plus b is less than or equal to the absolute value of an minus a plus the absolute value of bn minus b is less than epsilon halves plus epsilon halves is equal to epsilon for all n greater than or equal to n. Okay.
Why did we choose epsilon over 2?
Because I had to add them together. I got this is less than epsilon halves, this is less than epsilon halves, therefore their sum is less than epsilon. So I've got this is less than epsilon. Or this is less than or equal to that is less than epsilon. For all n from n onwards.
Why did we choose n as the max of n1 and n2?
Because this inequality right here is only true from n1 onwards. This inequality right here is only true from n2 onwards. So both these are true from n onwards if n's the max of these two. So if this is only true from 100 onwards, and this is only true from 256 onwards, then both of them are true from 256 onwards.
Yeah, but the reason we need both of them true was so that we could do epsilon over 2 plus epsilon over 2.
Yeah.
As
Ultimately, I need to find some index n such that this absolute value is less than epsilon from it onwards.
okay.
So I needed both these inequalities to be true from some index onwards.
Makes so much sense.
It makes sense?
Yes.
Wonderful. Because if you can get convergence, everything else from there on out is just as hard to get. But not impossible. It's impossible if you don't get convergence. So you're on track to keep on struggling. It's a great track to be on. Why am I looking at this? We can just look at what the next one is. Therefore, the limit of the sum is the sum of the limits. That's what we proved, right?
Yep.
Is there any question about that?
No?
Well, I do have a question about the previous proof that we did. So is this basically saying that the limit of 2 over n is equal to 2 times the limit of 1 over n? I'm just trying to connect it to one of the formulas that I used in my previous calculus class.
So you're saying, is the limit of 1 over n equal to the limit of what?
No, the limit of 2 over n equal to 2 times the limit of 1 over n. Like, you factor out the constant out of the limit.
Oh, factoring out the constant. Yes. So this happens to be true. So far, the way that we have to prove that is a comparison limit. I might not have written down the proof, but the fact that we can factor out a constant from a limit should be one of my proofs.
So this proof doesn't prove that exactly, it just,
Oh, I missed one of my proofs. So one of my proofs is the linearity property, which we'll prove after the quotient. So I am missing a proof that I should have in between here, which is going to say that this is true amongst other things.
oh, okay.
Okay, so far we have the sum of a limit is the limit of the sums. Or the limit of the sum is the sum of the limit. Same things, I just said it backwards from what's normal. Sorry, I'm erasing this. We good? Okay. Next one, we're proving if the limit of an is 0 and the limit of bn is 0, then the limit of the product is 0. So, one, where am I going to start? Let a and bn, so let those be sequences such that the limit of an is equal to 0 and the limit of bn is equal to 0. And we need to use that fact to show that the limit of an times bn is equal to 0. So let epsilon be some positive number greater than 0, some positive number. Note, we need to show, so what are we trying to show? We're trying to show that the absolute value of an times bn minus 0 is less than epsilon for all n greater than or equal to n for some n. Right? We need to find the big N that makes this true, and then we're done. Good? Okay, so let's see how we're going to prove that. 3. So let epsilon greater than 0. Let's just do some scratch work on the side. I'm going to get an times bn. I'm going to get that's less than or equal to an times absolute value of bn. And I'm going to get that is less than, remember I can make these less than anything I want since they converge to 0. So I'm going to get less than square root of epsilon times square root of epsilon. Epsilon is equal to epsilon. Okay, so that's how I'm going to go about doing it.
How do we know that an times bn is less than or equal to absolute value of an times the absolute value of bn?
That's the triangle inequality, right?
No, the triangle inequality tells us it for plus.
Right.
Or do we have to do a proof of this? Yeah, I don't have a way to justify it based off of what we did, but you know how you can prove this really easily, right? You're just going to handle the case where A and B are positive or negative. You'd have to handle the 4 cases, because there's going to be 4 combinations, well, 3 combinations really. And it's going to be true. And it appeals to our intuition, right? So I don't need to prove this, you know how you could go prove that. If A and Bn are both positive, yeah, this is true. If A and Bn are both negative, yeah, this is true. Okay, you have 1 positive and 1 negative. Well, then that's just going to be a negative for it. Plug in the negative makes it positive again. Okay, yeah, it's true.
I kind of get
Do we see it, or do I actually need to prove it?
Well, I get the idea. I don't know if I could go do it, but I know what you're doing. Like, it's the same way we did the triangle inequality.
We have 4 cases. So let's do an, bn, positive. Okay, then the absolute value of it, the product of 2 positive numbers is just positive. The absolute value of a positive is just the thing itself. The absolute value of both these are just going to be the terms themselves. Okay, in that case it's equal. Right? It's always going to be equal, actually. If one of them is positive and one of them is negative, the absolute value of the positive one is going to be positive. The absolute value of the negative one is going to be the negative of that. So you're going to have a negative on this side, but then you also get a negative on this side. Negatives go out, once again. And then, if they're both negative, it cancels out before we even take the absolute value here. Here, when we take the absolute value, there's going to be 2 negatives, they cancel out. So, it's equal. It's not less than or equal to, it's equal, but less than or equal is fine. Good? So now, let's see. What were we doing? We were doing an, that minus 0. Oh no, we needed to say an is going to be less than square root of epsilon, and bn is going to be less than square root of epsilon. So let's see. Since the limit of an is equal to 0, comma, then there exists some n1 such that absolute value such that an minus 0, which is just equal to an, is less than the square root of epsilon for all n greater than or equal to n1. Right? Since an converges to 0, I'm given that, then I can always find a natural number, namely n1, such that the absolute value is less than any positive number I choose. Right? That's what it means to converge. If an converges to a, what does that mean? Where do we have it? If an converges to a, then for any positive number you choose, I can always find an index big N such that this is true.
Why is it the square root though?
That's the positive number I'm showing it's less than.
Okay. Actually, it's count.
Because it's just positive number. Square root of epsilon is just positive number. Similar.
I don't see how the absolute value of an minus 0 is an? What if an is negative?
Oh, good catch. Thanks. Good now? Okay. For since the limit of Bn is equal to 0, comma, then there exists N2 such that absolute value of Bn minus 0, which is just equal to the absolute value of Bn, is less than square root of epsilon for all n greater than or equal to n2. Let n be the max of those. Let big N equal the max of n1 and n2. Therefore, both those inequalities are going to be true from big N onwards. 6. Then, absolute value of an times bn minus 0 is less than or equal to absolute value of an times absolute value of bn is less than square root of epsilon times square root of epsilon is equal to epsilon, that's an epsilon, for all n greater than or equal to big N, 7. Therefore, the limit of an times bn is equal to 0, right? Whatever, watch. Any weird steps? Anything confusing? Anything you don't like? Anything you just love and you just gotta sing about it? No judgment. I mean, almost identical to our previous proof. A lot of similar thinking, right? So we're just ready to move on to the next?
I guess so.
Well, could you have proved it assuming the other side of the equation instead of the one that you did?
We didn't assume a side. So,
to do
oh, sorry, we were doing an implication. We were showing that if this is the case, then this is the case. Is the inverse of this true? Is it true that if the limit of this is 0, then the limit of this or this is 0, or both is 0?
No.
And the answer is there's none. Because I can take sequences that don't even converge, namely, what? -1 to the n. There's one that doesn't even converge. And then another sequence, -1 to the n plus 1. So this one's -1 whenever this one's 1, and this one's -1 whenever this is 1. When you add them together, it's always 0. So there's some convert, or their product, oh, this is some. They want a product over there. That is different.
Yeah, because look, both of those proofs are like
If
switched, it looks
the
like.
product of two sequences converges to 0, does one of them have to converge to 0?
That doesn't say one of them does this, it's both of them.
I know, and it would have to be both, obviously. It just have to be one, right? Because I could let one sequence be this. Pick one that we know converges to whatever you want, C. And then pick the sequence. So here's one sequence. And then pick the other sequence, 0. Now take the product of those sequences. It's always 0. But this obviously doesn't converge to 0. It converges to picking number you want, 100.
That's only if...
The product converges to 0, but both the individual sequences don't necessarily converge
But that's
to 0.
only if one of the sequences is 0.
I could just, well, no, this would also work, 1 over n. Then the product of those two would still converge to 0. Because you get 1 over n squared plus 100 over n. So no, but if the product of both of them goes to 0, do I know at least one of them has to go to 0? That might be the case. I'd have to think about that more. But my gut instinct wants to say yes.
So yes, it's not just an implication, but
It's for sure just an implication because the inverse for sure is not true. I cannot say that this being true implies this is true. Because we just did 2 counterexamples. We picked,
isn't the limit of both of those 0?
no,
Each one of them?
the limit of this is 100.
Oh, right.
And the limit of this is 0. Their product is 0. And then also if I would have just stuck a 0 in for there, obviously the product is 0 where the limit of this is 100.
I see.
So, the inverse definitely is not true, but
If that was an or instead of an and, would it be true?
yeah, so that's what I was wondering, and that I'd have to think about. So I'm trying to think, can I come up with two sequences that don't even converge, but their product converges to 0? And my gut is I could. But I'm not sure. Anyways, so I'll have to think about it. What were we doing?
The fourth one, I think.
Oh yeah, the limit of a product is the product of the limits. Why do I keep grabbing this eraser? Just get it out of here. And let's see, am I getting you to use that previous proof in here? Oh yeah, this is a big one. So I want to do a lemma leading up to this proof. So maybe I'll do the lemma to the side over here and then do the proof. Oh wait.
We're probably not going to get through all of these today.
Oh no, I just missed another proof up there.
So we had 8 proofs.
Yeah, so we had 8 to get through. Yeah, 2.1 is a big section, so shoot, we're gonna get behind again. Okay, so for the product, that's how I'm gonna use the previous one. Okay, I see now. So let a_n and b_n such that the limit of a_n is equal to a and the limit of b_n is equal to b. That's 1, 2. What's 2 going to be?
Let epsilon and r.
Yeah, let epsilon be some positive real number, comma. No, we need to show that there exists some natural number, there exists some n in n, such that absolute value of a_n times b_n minus a times b is less than epsilon for all n greater than or equal to n. Right? Once we show that, then it will have been proven.
We're doing the fourth proof there.
Yeah, we're proving that the limit of a product is equal to the product of the limits. So I'm showing that the limit of a_n times b_n is equal to a times b, where that a and b_n converges to a times b. Good? Okay, so I'm going to use my previous proof, this proof, where if I have 2 that converge to 0, then I know that their product converges to 0. So I'm going to use the fact that I know that a_n converges to a and b_n converges to b to create 2 sequences that I know converge to 0. 3. Find alpha n by, well, we'll just write it, alpha n equal to a_n minus a and beta_n equal to bn minus b.
So I'm a little confused about what you're doing there. What is alpha n minus a? I mean, sorry, an minus a.
What is an minus a? Oh, it's a sequence. So let's come up with the example real quick. So a sequence that converges to 1 would be, so let's pretend that an was a sequence. An was equal to n plus 1 over n, right? This converges to 1. So I'm saying let's define a new sequence called alpha n then. Alpha n, and what's alpha n? Alpha n is now going to equal n plus 1 over n minus 1. So notice that this one tends towards 1, this one tends towards 0. Right? So define that, comma, and note that the limit of alpha n is equal to 0, which is also the limit of beta n. Right?
Yes.
Because what's the limit of alpha n? It's the limit of this plus the limit of this. What's the limit of this? Negative a. What's the limit of this? A. A plus negative a? 0. Right? Just using the fact that the sum of the limits is the limit of the sum. If you want to think about a is just a series a. We good so far? Okay, so we have an and bn, or sorry, we have alpha n and beta n are two sequences that both converge to 0. So so let's go back to what we were trying to show is ultimately less than epsilon, I think. So then, an times bn minus ab, let's see what that's equal to in terms of alpha and beta. If alpha n is equal to an minus a, then an is just going to be alpha n plus a. Right? So I can rewrite this as alpha n plus a, and then this one's going to be beta n plus b minus ab, which is equal to absolute value alpha n times beta n plus a beta n plus b alpha n plus AB, that's expanding them all out, minus AB. The AB's go out. This is equal to, are you good with all the algebra there? It's just distributing.
I'm confused how you substituted alpha n plus a for an.
I mean, I put these here to help you realize that we're defining a sequence, but maybe they're just confusing you.
Are they not defining a sequence?
They are. But this is just saying that the nth term is equal to this. So this is true for, when you plug in 1, then alpha sub 1 is equal to a sub 1 minus a. When you plug in 2, alpha sub 2 is equal to a sub 2 minus 2. So in general, a sub n is equal to alpha n plus a. Right? Just plus a to both sides, plus b to both sides.
I was thinking of it like a sequence, so I was wondering why you could just plus.
Yeah, we're just saying how we get the nth term in a sequence. So we're still talking about a particular term, and so you can make these substitutions.
Okay.
So you get now? So those are going to go out, and then let's use the triangle inequality to split this up. Plus not equal, less than or equal.
There we go.
Good with that?
But they're all the same sign, right? If they're all the same sign, aren't they equal?
Let me think. Sorry, yeah, we should have been using limits. Oops, oops, oops. I'll rewrite it underneath. Ignore line 4, but I'm going to rewrite it. You'll just see. So then the limit of an times bn minus ab is equal to the limit of substituting in the alphas, doing the algebra. So I'm going to skip straight to just writing this with the ab's canceled out. Forget the triangle inequality. Forget that. We can just call 5 and say we're using the previous line. So then the limit of that is equal to the limit of alpha n times beta n plus a beta n plus b alpha n. You good with that? We can get rid of all these absolute value signs. I was just making this substitution now. So I'm saying the limit of this is equal to the limit of this. Let the AB and the negative AB cancel out. That's all I'm doing.
Okay.
And then we know that the limit of the sum is the sum of the limits, etc. So using our limit properties rather than trying to prove this directly. So I probably didn't even say let epsilon greater than 0. Yeah, I didn't even say epsilon.
I do have a question.
Yeah?
We have
So we're not even.
alpha n and beta n. We have the limits for those. And
So
we have them equal, look, and we have them equal to that right there. So technically, couldn't we say that the limit of an minus a is 0?
Yeah, I know that the limit of an minus a is 0.
Right.
Yeah.
Isn't that what we're trying to do?
No, I'm trying to show that, so 2, need to show that the limit of an times bn is equal to 0. I should have looked at my notes better. Sorry. So let a and bn be sequences such that a converges to a and bn converges to b. What am I trying to show? Sorry, not converges to 0, converges to a times b. I'm trying to show that the limit of an times bn is just a times b. Right? And rather than proving this directly like I was doing before and going back and forth between my notes making a mess, we're not going to prove it directly, we're just going to use stuff that we've already proved to do it now, instead of going all the way back to the definition of a limit. Okay, so what do? I define alpha n to be this, beta n to be this, and we note that the limit of alpha n is 0 and the limit of beta n is 0. Make our substitutions. A n times bn minus ab that's another proof that we need to do. Where am I? Oh, I had it as a side note here. So this is a homework problem that you're going to do, which we're going to use real quick. Shit. Sorry. So homework. You're going to prove that the limit of an equals the limit of an equals a is logically equivalent with the limit of an minus a is equal to 0. So if the limit of an minus a equals 0, then the limit of an equals a, and vice versa. That's what you're going to prove. And that way, we need to show this, which is logically equivalent to showing that the limit of an times bn minus ab is equal to 0. Okay.
That makes so much more sense.
Now I see where I'm going with all this. Okay, so this is the homework problem that you're going to do. So you understand what the homework problem is going to give you, right? It's pretty intuitive. if an converges to 5, then an minus 5 converges to 0. Right? And vice versa. That's what you're going to prove. So, we're proving that if an converges to a and bn converges to b, then the limit of an times bn is equal to a times b. How we're going to prove that is we're going to prove that the limit of an times bn minus ab is 0. Once we solve this and we solve this because they're logically equivalent due to your homework problem. Okay, so then we define alpha n to be an minus a and beta n to be bn minus b. That way the limit of alpha n is 0 and the limit of beta n is 0. Now we can rewrite what's inside this limit here, an times bn minus ab. We can rewrite that in terms of alpha and beta this way. Simplify, simplify gives us this. Finally, a, b, these two cancel out, giving us alpha n times beta n plus a beta n plus b alpha n. Okay, so then the limit of an times bn minus ab is going to be the same thing as the limit of alpha n beta n plus a beta n plus b alpha n. Right? You have to be kidding me. We still missed a proof. Alright, we're going to finish it using what I'm going to go back and prove in a second here. So this is equal to the sum of the limits. This is the limit of an times bn, or sorry, alpha n times beta n, times beta n, plus the limit of a times beta n, plus the limit of b times alpha n, right? The limit of the sum is the sum of the limits, is equal to, what's the limit of the product of these two? Since alpha n goes to 0 and beta n goes to 0, then their limit product goes to 0. That was a previous proof, right? That was this. If we have two limits that converge to 0, then their product converges to 0. Alright, both these go to 0, so then this goes to 0. Plus, here's what we're going to prove in a second. When you have the limit of a constant times a sequence, you can pull the constant out. When you have a limit times a constant times a sequence, you can pull the constant out.
These are really similar to logarithmic properties.
Kind of. So this is the same thing as a times the limit of bn plus b times the limit of, not bn, that's alpha, or beta n, and b times the limit of alpha n, which then again is going to be 0 plus 0, so it's all equal to 0. So I need to prove that we can pull the constants out, but assuming we have that proof, you see how we showed that this converges to 0? And that proof is going to be a quick little two-liner.
Cool.
So, prove that if the limit of an is equal to a, comma, then the limit of alpha times an is equal to alpha times a for alpha in R. So for any real number alpha you pick, for any alpha you pick, for any real number you pick, if an converges to a, then an times that real number converges to a times that real number. You understand what we're proving? And then this is obviously just going to use a comparison number real quick. So 1, observe that the absolute value of alpha times an.
So in this one, an is a sequence?
Yeah, so an is a sequence that converges to a.
so the alpha
is just some real number.
is the constant.
Yeah, we could have picked, maybe a C would have been better, since we did alpha weird up there.
Yeah.
So we'll put a C, 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 just some constant. Oh, no, you do it here. C, C. So let A and B a sequence that converges to A, and let C be any positive number. Forgot to write that first. That should have been my first line. Then this is my second line. Observe that C times AN minus CA is equal to, well, less than or equal to, is equal to the absolute value of C times the absolute value of AN minus A. Notice if we factor out the C before, then it's just C times something, and the absolute value of a product is just product of the absolute values. That's the same discussion that we had before up there.
Wasn't that an inequality, not?
I put it as an inequality and then erased it because it's just equal.
That's something that we proved.
So once you factor out the C, it's just C times something, and the absolute value of the product of two things is the same thing as the product of their absolute values. Let's see, where was that little proof? Is equal to that, and then is less than or equal to that. Why am I saying that it's less than or equal to that? Just to stress the fact that we're using the comparison lemma. So 2, since the absolute value of C is greater than or equal to 0, then my comparison lemma then the limit of C times AN is just equal to C times A. So let's make sure we understand this real quick. What does the comparison lemma say? The comparison lemma says that if AN minus A, if AN converges to A and C is any number greater than or equal to 0, and if this inequality holds from some index onwards, then Bn converges to B. So this inequality holds, we could have said for all n greater than or equal to 1, to stress that. This is always the case.
How do we know that's, you said the absolute value of C. Never mind.
Yeah. So we just did the absolute value of C. So we have Bn minus B is less than or equal to a constant times AN minus A for all n starting at some index. Since AN converges to A, then Bn converges to B using the comparison lemma. Does that make sense? Sorry, that proof was a nightmare. Went all over the place.
Honestly, I feel pretty confused about this entire proof.
About the product one?
Yeah,
Are you good with this one?
I think so.
Alright, then let's just redo the product one real quick from scratch. This way I won't throw you all over the place. Because we need to use this proof. We need to use a proof where if two sequences converge to 0, then their product converges to 0. And we need to use what you're going to do in your homework, which is that if the limit of AN is A, then the limit of AN minus A is 0. So those are the three proofs that and we're also going to use this proof, that the limit of a sum is the sum of the limits. So we're bringing the 4 proofs together in this one proof. Okay? So here's this. 2. Observe that the limit of an times bn equal to a times b. This is what I'm trying to show. I'm trying to show that this is equal to this. Right? So observe that we've shown that this is true, or this is logically equivalent to showing that the limit of an times bn minus ab is equal to 0. That's using your homework proof.
Okay, where did we get that first part? The limit of an times b is a times b.
We don't know that. That's what we're trying to prove.
How do you know they're logically equivalent then?
How do I know that this is logically equivalent to this?
Yeah.
That's what you're going to prove in your homework. You're going to prove that if the limit of an equals a, then the limit of an minus a is 0. So if this is the case, then this is the case, or better yet, if this is the case, then this is the case. So I'm not going to show this, I'm going to show this. And then once I've shown this, I've also shown this and we're done.
Okay.
So now this is where I'm trying to get. With me?
Because we haven't proved either of those statements, but we're using those statements to
We're using the fact that they're logically equivalent. We're saying, I'd rather prove this than prove this. It's like, I'd rather use a contrapositive than a direct implication kind of.
We do it the other way.
That means on homework we can't use this to prove that.
No, on homework you cannot use it to prove itself. That is correct.
Shoot.
Okay, so 3. Define alpha n equal to an minus a and beta n equal to bn minus b, and denote that the limit of alpha n is equal to 0, which is also the same thing as the limit of beta n.
So are we treating those like sequences or like numbers?
It's a number when you plug in a particular n. How do I get alpha sub 3?
Plug in 3 for n.
Plug in 3 for here. And subtract away a. That's alpha 3.
But is it a sequence?
Yeah, alpha sub n is a sequence.
Okay, and what proof are we using to show that their limit is 0?
We can just observe that real quick. I mean, we're using the fact that the limit of the sum is the sum of the limits. The limit of an is a, the limit of negative a is negative a. Add those together, 0. We're assuming that you can do that in your head.
Alright.
But we could have added a line if you want.
Okay.
So you're good with that? Or do you want me to prove that?
I think we're good.
Okay. So then moving on to 4. Then the thing that we're working with, what's this? So then the limit of an times bn minus ab, if we write this in terms of alphas and betas, is going to be the limit of alpha n plus a times beta n plus b minus ab. Right? If alpha n is an minus a, then an is alpha n plus a, and vice versa. And similarly for substituting in bn.
And why are we doing that?
To get in terms of alphas and betas, to get in terms of sequences that we know converge to 0.
Okay.
So then this is equal to the limit of alpha n times beta n plus a times beta n plus b times alpha n plus ab minus ab, just multiplying it all out. Okay? And that's equal to, the a's and the b's cancel out, and I'm going to split it up into individual sums. That's equal to the limit of alpha n times beta n, I meant break up into individual limits, plus the limit of a times beta n, plus the limit of b times alpha n, which is equal to, we know that the limit of two things that go to 0 is 0. Now we're using this proof. So we know that this is 0. Plus, we know that the limit of a times bn, or a times beta n, is equal to a times the limit of beta n. That's using this. If a n converges to a, then a n times a constant is just that constant times an a. So this is just equal to a times 0, and this is just equal to b times 0 is equal to 0. And we're done. We showed that this limit is equal to 0. This limit equaling 0 is logically equivalent to this limit equaling ab, which is what we're after. Good? Okay? Alright, make sure I didn't miss anything else. So we did the sum, we did times a constant, we did if they both go to 0, we did the limit of a product, and now we're doing proof that if the limit of bn is equal to b, and b is not 0, then the limit of 1 over bn is equal to 1 over b. Yeah, we don't have time to do that. Maybe we'll just cover intuitively the rest of them real quick, and then we'll finish proving next time. So the next proof is to prove that the limit of bn equals b, where b is not 0, implies that the limit of 1 over bn is equal to 1 over b.
Okay.
So
Is not
the limit of the inverse is the inverse of the limit. The multiplicative inverse, the limit of the multiplicative inverse is the multiplicative inverse of the limit, is one way that you can say that.
Is there a proof that will show that the limit of 1 over an is equal to the limit of 1 divided by the limit of an, or the limit of 1 minus
No, we
1
won't,
an?
because we'll use this limit to then show this limit. Then we'll show out the limit of an over bn is the limit of an over the limit of bn,
Yeah.
which you can then just use that for the specific case that you're talking about. Right? And then, make sure I'm not missing anything. Yes, missing something. So then before we do this, we'll prove the linearity property. That is, we'll prove that the limit of an equal to a and the limit of, not beta n, of bn equal to b.
To be.
That was weird. To b, thanks. And if alpha and beta are real numbers, so all of this implies that the limit of alpha times an plus beta times bn is equal to alpha times A plus beta times B.
Which is, yeah.
Huh? So we'll prove that, and then we'll prove, finally, this. For any polynomial x, if an converges to a, then the polynomial, when you plug in an, converges to p of a. You know what a polynomial is?
No.
An example of a polynomial is something like 3x cubed plus 2x squared plus 9. There's a polynomial.
That doesn't tell us what a polynomial is.
No, there's a polynomial. A polynomial is going to be a sequence of exponents. So, in short, a polynomial is going to be anything of the form that could be written as a sum from k equals 1 to n of a sub k times x to the k. Where these are just real numbers and it's always x to an exponent. So if I can write it as, write this out, if I can write it this way, a sub 1, a sub 0, sorry, we need to start at 0. If I can write it as a sub 0 plus a sub 1 times x to the 1 plus a sub 2 times x to the 2 plus dot 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 plus a sub n times x to the n, then it's a polynomial where all these are just real numbers and the n is obviously naturals.
And that's like the actual definition of polynomial, right?
Yeah, anything written in that form. We'll come back to.
When you're plugging in an to the polynomial p, is it like the nth term of the sequence an, or is it the whole sequence?
You're plugging in the whole sequence and it gives you a sequence, right? So let's write one out to see it, and we'll pick a simple polynomial n. So what is this saying? So let's take a sequence that converges to, so we'll do an, let's take one that converges to, I don't know, 1. So we'll do our n over n plus 1. There's an, right? And a in this case is equal to 1. And let's pick the polynomial. Let's keep a simple polynomial. We'll do something like, I don't know, 2x plus 1. A really simple polynomial. Then, what is p of an? First, when you plug 1 in for here, what do you get? 1/2. Then when you plug 1/2 into here, what do you get? 2. So the first thing I get, my first term in an is 1/2.
So
When I plug 1/2 into my polynomial, I get 2. You see that?
your polynomial is a function, basically.
Yeah, polynomial is a function. It's a special type of function.
So in your function, you're plugging in sequence.
Yeah, I'm plugging a sequence an into my function, taking the limit of that, and I'm saying I'm going to get the same thing I would have gotten if I would have just plugged in the limit. So my first term is 2. Now let's figure out my second term. When I plug 2 into this, what do I get?
2/3.
2/3. Over here, 2/3 times 2 is 4/3.
7/3.
Plus 1 is 4/3. You're right, 7/3. Right? Let's do 3. We get 3/4. Did I do that right? Yeah. 3/4 times 2 gives us 6/4, gives us 10/4, or 5/2, right? Let's plug in 4. We get 4/5 times 2 is 8/5, or 13/5.
not seeing where it's converging to yet.
Okay, so let's skip ahead some and plug in 100. So I plug in 100, what do I get? I get 100 over 101, or times 2, I get 200 over 101, plus 101. So I get 301
So it's
over
converging to 3.
100. Yeah, it's converging to 3. Right? So we're saying whatever this is converging to, this sequence. So there's P of an. We're saying that the limit of P of an, rather than going through all the hardship of figuring out what the sequence is, we're saying it's just equal to P of the limit of an, which is just P of A. So in this case, what's P of A equal to? 3.
What is A?
1. It's whatever AN converges to.
Oh.
AN converges to 1, plug 1 in, it's 3.
Oh. Well, that was fancy.
So for Emma, since she's already done calculus, this is what you were doing when you were talking about the limit of a function as it approaches a point. Behind the scenes, what do? We take a sequence that converges to that point, then we plug into the function to figure out the limit of the function as it approaches that point. So this is how we can talk about the limit of a function as it approaches a point without actually getting to the point. Because notice, AN in this case, AN's never equal to 1. Right? It just gets really, really close to 1.
Right.
So I never actually plug 1 into this function.
Okay.
So I could have a function, I mean you did this, I guess some of you didn't do trig. Did any of you do trig? You maybe did in algebra 2, where you had functions, and the function suddenly had a hole where they weren't defined.
Right.
So we can still talk about the limit at that point, even though we can't talk about the function's value at that point.
How does that work?
Because we never, when we take the limit, so let's say that this hole was at 1, right? And let's pretend that that squiggly line I drew is actually 2x plus 1, even though it's obviously not. So let's pretend that our function wasn't defined at 1, but we want to take the limit of the function at 1. How do we do that? We pick a sequence that converges to 1 and plug that in for the function. And we take the limit of that resulting sequence. So notice, I never plug in 1 to this function.
Because you can't.
I just plug in n over n plus 1. I plug that series in, or that sequence in.
Oh, I see now. Okay,
Because it
so,
converges to 1.
well, I did in that calculus class, or like in the very beginning, it was like plug in 0.9, plug in 0.999, and is that the sequence that converges to 1 that you're talking about, that you plug into the function?
Yeah,
Okay.
it could have been. Yeah,
I'm just trying to make the connection between what you're saying and what I did.
yeah. This behind the scenes, this is what you were doing.
Alright.
Can you explain that one more time?
So
So that's,
AN never plugs in 1,
but it can get really close.
but it gets really, really close to 1. So this function, which might not be defined at 1, we get points that get really, 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 really close to what it is at 1. And so we talk about what that function gets really, 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 really close to is its limit there, even though the function is not actually defined there. Because I can't plug 1 into a function if it's not defined at 1. If I can plug in numbers really, really close to 1, I can plug in numbers as close to 1 as I want. In fact, I can plug in infinitely numbers that get arbitrary close to 1.
Right.
Namely, a sequence that converges to 1. And I can look at that function at all those points, which gives me another series, and then I just take the limit of that.
What's
So
the
there's
best
an
way-
infinite
what's the
amount of
point of getting
numbers
the limit
between
of that?
numbers.
Yes. What?
What's the point of getting the limit of that?
The limit of a function at a point? We'll get there. It's very useful.
So, what this is doing is we get. Well, I guess I'll understand later.
Yeah, we're skipping ahead a lot to motivate where it was going.
Like, I get kind of what you're saying. I'm not seeing where it connects to this.
We never plugged 1 into this polynomial.
Right.
But we figured out the limit of this polynomial as it approaches 1. So even though we never plugged in 1, we figured out its limit as it approaches 1.
what does that mean though?
We never had to plug 1 into the function to figure out its limit as it approaches 1.
What does that look like on the graph? Does that mean that?
It could be a hole like this, for it to not be defined there. There could be asymptotes involved.
But does that mean that it gets to, that your y-axis is 3? Well, if your limit is 3.
Oh yeah, so yes, you're exactly right. So based off of that, then yes, the height of that point is 3. That's what we mean. So even though there's a hole there, we can still figure out the exact height of that hole. Because we couldn't plug in 1 to the function to figure out what it was, because the function's not defined there.
So you want to do that with limits. is the
So
idea.
now we have limits. So we don't need to throw functions out just because they have holes in them.
Well, can't you figure out the hole just by, well, I mean, does
By
that,
looking at it.
well, what we did, it probably doesn't work for everything, but in college algebra, you have those removable discontinuities all the time, and you just,
Right, you had it for special types of functions, but then what if I took a function like f only goes from the interval 0 to 1 to the real numbers, so I can't plug 1 in this case, and now I want to figure out by f of x is equal to, I don't know, 3x squared plus 2, something easy. The point is, now I want to know what's the limit of this as we approach 1.
so the.
And I couldn't plug
when
1
you
to the
say
function
that,
because it's not in
that
the domain.
means what number is that getting really close to as your x's approach 1?
Yeah. So you know from looking at it, based off of your intuition, oh, that's just going to be 5.
Oh, sure. Why do I know that? Because when you plug in 1, you get
Because when you plug in 1, you get 5.
3 to 5. Oh.
You said you didn't plug in 1 over there, but did P of A is P of 1, which is 3. Didn't you just plug in 1?
P of A is P of 3.
It's P of 1, because A is equal to 1.
Oh, yeah, so you can always figure out what the limit is just by plugging in a point.
Oh, I thought you were saying you didn't plug it in.
I was just making note that we didn't plug it in over here.
So, P of A is.
I'm not saying that this is how you calculate the limit. I'm saying notice that it's possible now to take the limit of a polynomial. We'll get into this more. We're skipping ahead a lot.
Okay.
It was just making a
connection.
mention for something that we're going to come across later down the road. But yeah, we'll go over that again. You understanding exactly what the polynomial is and what we're proving is actually the hardest part of that. So if you
Yeah,
understand
I'm
that we
struggling with
basically
that
took
a little bit.
this sequence and reconstructed this sequence from it, and then just took the limit of this sequence, that's the hard part when I do the proof.
I'm not used to thinking of a polynomial as a sequence, so it's just.
Polynomial is not a sequence. A polynomial of a sequence is a sequence.
Yeah. That is so weird.
Okay. We'll come across again.